we're changing gears here, going from electricity, electromagnetism, and electromotive force, and we're going back to chapter 12 and also to chapter 13 after this. We're looking at a concept called specific heat, and we did one lab a while back when we heated both zinc and copper, and we attached little wax pieces to them, and we put them in a beaker of some hot water, and we tried to see which of the beads melted the first. And the copper should have melted first, and the zinc should have melted second. And that's because while copper is a good conductor of electricity, it's also a good conductor of heat. So every material has a different ability to transmit and conduct that heat, and that's called the specific heat. So specific heat is identified with a capital C, not to be confused with coulombs or with Celsius or any other capital C. So let's go ahead and give a definition of what specific heat is. So specific heat is the energy needed. So it's the energy that's needed to increase a mass of material by 1 degree. And when I say 1 degree, I'm going to be saying either a degree Celsius or a degree Kelvin. Now that degree actually is a little bit not needed there because it's just Kelvin, but just to show that it's actually degrees Kelvin. And if you remember the Celsius and the Kelvin scale, these are off by about a factor of 273. But every 1 increase or decrease in degrees Celsius is the same as 1 degree increase or decrease in Kelvin. Very different for the Fahrenheit scale. So mostly what we're going to be doing in this lab is we're going to be taking the change in temperature. So it's going to be the change in Celsius or the change in Kelvin. So a change in temperature of 10 Celsius is going to be the exact same as the change in Kelvin as well. So let's take a look at the units. It's the energy needed to increase a mass of material by 1 degree. So the units for specific heat are going to be very important, and the units are going to be joules over kilogram degree Kelvin. And again, that degree Kelvin could be or degrees Celsius as well. Let me go ahead and give a specific heat for copper. The specific heat for copper is going to be 385 joules per kilogram degree Kelvin. Meaning if you have 1 kilogram of material, it will take 385 joules to heat it 1 degree, either Kelvin or degrees Celsius. Let's take a look at the specific heat for water. This is a very important number because just as the temperature scale, the units of masses, and the units of volume are all dependent upon water, so is another scale, and we're going to be taking a look at that. And what we have is we have 4,180 joules per kilogram degree Kelvin. We're going to come back to that specific number in a minute, but let's take a look at comparison. Why is the water higher than the copper? Well, we said that copper is a good conductor of heat. Water has the ability to retain heat, but it's going to take a while for water to heat up. And if you remember from chemistry, this has to deal with the hydrogen bonding of water. Remember, water has this bent shape. It looks something like this. And it has these magnetic attractions between them, or these electrical attractions. And this is the hydrogen bond that exists between 2 water molecules. So if you remember, to increase the temperature of something, you actually have to increase the kinetic energy, or you have to increase the velocity of the particles. So to increase the temperature, since this is based upon increasing our temperature scale, to increase the temperature of anything requires you to do this. We need to increase the kinetic energy. This is not Kelvin, that's why I'm kind of doing degrees Kelvin here. This is the kinetic energy, and by increasing the kinetic energy is 1/2 mv squared, meaning we have to increase the average kinetic energy of each particle, meaning that we have to increase the velocity. Well, these water particles are electrically attracted to each other because we have these partial negatives and partial positives, and it forms this magnetic attraction. Water likes to stick to itself. In order to get these to be more freely moving around each other, we have to break that hydrogen bond. So why does water have such a high specific heat? It's because we need to add more energy to break that hydrogen bond. So we need more energy to break that hydrogen bond. Once you break that hydrogen bond, then these water particles are able to more freely rotate around each other, and the water is going to be then free to spin faster. So again, that's why the specific heat of water is so high compared to copper. Let's take a look at the concept of heat. We're going to be using this formula quite a bit during this chapter. Heat is going to be represented with the symbol capital Q. And heat is going to be equal to the mass of an object times the specific heat times the change in temperature. Meaning, heat is going to be a transfer of energy from something that's hot to something that is cold. That's dependent upon the mass of your object, the specific heat of the object, and how much are you actually increasing the temperature. Let's take a look at the units of this. The units of mass are going to be kilograms. The units of specific heat, we have it over here, it's going to be joules over kilogram degree Kelvin. And we're multiplying this by the temperature, which is going to be the degrees Kelvin. And what you'll note is that the kilograms cancel, and then your degrees Celsius or your degrees Kelvin will cancel, and you're left with joules. So heat is actually measured in joules. Heat is energy being transferred from a higher to a lower energy. So it's going to be measured in joules. So earlier I had said this is an important number, this 4180. We're going to go ahead and take a look and see why this is so important. So we're going to be getting into food, and food energy is going to be measured in calories. 1 calorie, and make sure that you're using a lowercase c for this. 1 calorie has a amount of energy that is 4.180 joules. Again, that should look familiar because we have the specific heat of water is 4,180 joules. So even our food calorie system is based upon the amount of energy that's needed to increase the temperature of water. So now if you have 1,000 of these calories, so if you multiply this by 1,000, now we have 1,000 little lowercase calories. That means I have 1 kcal Just like if I have a meter and I have 1,000 meters, I have a kilometer, this is 1 kcal. Okay, so 1 kcal is going to be equal to 4,180 joules, which again is the specific heat for water. And this is equal to 1 capital C calorie. This is our food calories. So 1 food calorie is going to be equal to 4,180 joules. Do you guys remember in chemistry, the gummy sacrifice, and how much energy was released from that very small amount of gummy, the gummy sacrifice? So that is showing you the amount of energy that's being released. We've got a lot of joules, a lot of energy is being released from food. Okay, so let's take a look at heat and where heat is being moved around. There's actually, we can have a positive heat, we can have a negative heat. If you have a positive Q, that means that you have absorbed heat. And if you have a negative Q, that means you have lost heat. We're going to be doing these heat calculations, so that's very, very important for understanding where this is going. So, for example, there's going to be 2 scenarios, just to give you some examples. Let's say you have some ice water. So here's your cup or your beaker, and here's your ice cube, and it's floating. Okay, if you remember from chemistry, heat goes from hot to cold. And so the heat is hotter in the water. There is heat in the ice, there's just less heat. And so the heat is going to travel from the hotter to the cold. So this is the direction that the heat moves. The heat that is gained by the ice is going to be equal to the heat that is lost by the water. So the positive Q, because that's going to be the heat being absorbed in the ice, the positive Q in the ice is going to be equal to the negative Q that's being lost from the water. So in this case, the ice is absorbing the heat, so therefore it's going to melt, and the water is going to lose the heat, and so the water is therefore going to cool. Again, we talked about this in chemistry, and it's called evaporative cooling. If you remember, if this is your skin, and here's a globule of sweat. Here is your liquid sweat, and what happens is this liquid begins to evaporate, and it becomes a gas. Where does the heat come from? The heat comes from your skin to make this evaporation process work. So here's the movement of the heat. So what happens is we have the positive Q of the sweat is going to be equal to the negative Q of your skin, meaning your sweat is going to absorb the heat, your skin is going to lose that heat as well. Excuse me. So I want to take a look at the 3 phases real quick, and we'll conclude on this for this portion. Remember, we have solid, and we have liquid, and we have gas. Those are the 3 phases of matter. There's actually 4 with plasma, but we're just going to focus on these. How do you get a solid to a liquid? It has to melt. You have to add energy in. How do you get the liquid to gas? You have to add your energy in. So when you are going from a gas to a liquid, okay, you're condensing. When you're condensing, energy is actually going to be released if we're going in the reverse process. So again, going from solid to liquid, melting ice requires energy, boiling water requires energy, so the reverse process must be true. Going from liquid to solid, that makes a little bit more sense. We have to take the energy out. We have to take the energy out of the liquid to make it cool enough to freeze. Then it'll be forming a solid. So this is actually related to clouds and a misconception about clouds. And the question is, why do clouds float? Well, clouds float not because, oops, we lost my lights. Clouds float not because that these particles are less dense than air, because we're actually taking gaseous water and we're making it to a liquid, and liquid water is more dense than the surrounding environment. So if you have your ground here, if you remember we talked about this when we were looking at lightning, the heat from the sun, especially in these most recent days, is coming to the earth and we're getting more and more sun. This causes the ground to absorb the ultraviolet radiation and visible light, and it re-radiates that as infrared heat. So we have this gaseous water, and it actually, you cannot see it because it's gaseous water. And then when we reach a certain level of the atmosphere where it's cool enough, okay, let's just say here's where it gets cool enough for it to condense. What's going to happen is then we form water droplets. We form liquid water particles. Now we can actually see the cloud. So a cloud is not gaseous water, it's actually liquid water droplets. This now actually forms and makes the cloud. But if you look to see what has happened, we've taken this gaseous water and we've made it liquid. What's happening in this process of going from gas to liquid is the energy is coming out. To make a gaseous water into a liquid, the energy is going to be coming out. Well, it's coming out of the gas particle. Where is that energy going? The energy that's coming out goes into the air. So we have the heat being lost into the air. So we have a positive Q for the air, and we have a negative Q from the water because it's going from gas to liquid. This is losing the heat, this is gaining the heat. So because we're heating the air, what happens is whenever you heat something, most often than not, it's going to decrease the density. Remember, density is equal to mass over volume. When you heat the air actually is going to expand. That's going to decrease the density. So the volume of the air is going to expand and the density of the air is going to decrease. And that decreased density of the air surrounding the particles is actually enough to suspend the cloud. A cloud is very, very massive. It weighs hundreds of trillions of tons. But the surrounding density of the air helps to make it buoyant.